Thank you, everyone, for attending this webinar. So good morning. So I'm Yves Fremat, so I'm developing the ESP-ELS and ESP-HS algorithms. So during the first CU8 webinar, you mainly saw how the generalized stellar parameterizers and Flame were deriving the astrophysical parameters and fundamental parameters of the majority of stars. So I will mainly explain the work that we have done and the results obtained by more focused processing, specifically of hot stars and emission line stars. So this processing is done by ESP-ELS and ESP-HS. ESP stands for Extended Stellar Parameterizer, ELS for emission line stars, and HS for hot stars. So I guess you see my my mouse? No? You don't see my
Yes.
Yeah? Okay, thank you. So here I took the I took back the same figure that Hosanna was presenting. So it's the workflow. So it's a very simple workflow of the APSIS pipeline with somewhat adapted workflow diagram of the ESP. So what is important here in this diagram is the lower part, which is gathering all the modules that are treating the spectra of stars. So an ESP is arriving here at the very end of this workflow, because ESP is in some cases also using parameters from GSP-FOT and GSP spec. Also within the ESP chain, we launch the modules in a particular order, so which is given here from the top to the bottom. So, and that's mainly important for the HS module here, because the hot star module is only launched on A, B, and O type stars. So, and it needs some information from the ELS package to decide to process some data from the input that is provided to the module. It also uses some information from the ELS to decide how to process it also. Here on the right, I listed the output that is provided by these these two complementary modules. So these results are saved in the saved in the main astrophysical parameters table here. And these results are mainly relative to the emission line stars. So it first also provides a spectral type tag. So why it provides, so the main reason why it provides a spectral type tag is that it's, for example, used by this hot star module, and it also provides some class label for the detected emission line stars, as well as measurement of the H alpha line things for most of the input targets, so including cool and hot stars with or without emission. The hot star package is really a stellar parameterizer, which provides the astrophysical parameters of the stars. So it provides effective temperature, surface gravity, interstellar extinction, and when the RVS data is available, it also provides an estimate of the line broadening in the RVS spectrum. The ESP, ELS, and HS modules did not run on the complete data that was available. There has been some compromise found just to avoid that the modules processed data that are too faint or of too bad quality for the algorithms, and also for a question of processing time, it has been decided to implement a straight magnitude cutoff at magnitude 17.65. So if you compare here, so that's the counting of targets as a function of the magnitude. So if you compare it with the other modules, you see here that there is this straight cutoff in, for example, the distribution of the spectral type that is provided, spectral type tag provided, and also the astrophysical parameters provider or the ELS class label. So this is the outline of my presentation. So throughout my presentation, I will follow really the workflow that we have in APSIS. So meaning that I will start by giving some details about the ELS algorithms. So I will discuss the methods and so the assumptions and the results that have been obtained. Then I will proceed with the hotstar module. Same, I will proceed with detailing some assumptions that have been made, and also some quality assessment of the results that we obtain. So the last slide that I will show is just providing an overview of the output of the two modules, as well as some additional features we plan to add for during the cycle 4 of the data processing. So about the emission line star module, so one important thing to keep in mind is that APSIS, at least during cycle 3, only processed coadded spectra. So that's the case for the BPRP data, and also for the RVS data. Specifically about the BPRP data, we also have to keep in mind that we do not have access during the processing to the externally calibrated data, meaning that we are directly working on this bell-shaped energy distribution that we also see. So that's the internal calibrated version of the spectra, so that we can also see delivered with the DR3 catalog. So we are directly working on this bell-shaped energy distribution. So in order to make the processing a bit more robust in the emission line stars, because we plan to extract some specific features and to normalize these features, we need to correct for this response function of the BP and RP bandpass filters. So, and that is done by dividing the spectra by a mean response curve. So that's what you see here on the right here. So we see the spectra of different types of emission line stars that have been divided by this mean response curve. So on the left, you have the BP passband, and on the right, you have the RP passband. So for example, we see here that the H-alpha feature is overlapping in the two passbands, but at the resolution, the effective resolution of the spectrum at the edges of the passband is different. So at the red edge of the BP, we have a lower spectral resolution than on the blue edge of the RP passband. Meaning that when we decide to extract, for example, the H-alpha line, we will mainly take the version that we find on the RP spectrum, which also has some drawbacks because here we are at the blue edge of the RP passband, which response function is dropping very rapidly, meaning that the precision of the mean response curve we use to correct the spectrum has also a lower accuracy in that region. So that has some negative impact on the measurements we are making, of course. So in the ESP-ELS package, we do not work directly on the complete BPRP information. We decided to extract the most pertinent information. So we decided from a list of emission features to extract from the BP and RP data. So we extract these features and we normalize these locally. So the goal being, so since the classification is based on a series of random forest classifiers that need to be trained on observed data. So in the case of emission line stars, we need to use observed data, and that we are lacking some reference spectra to train the random forest on. We try to use most of these spectra, but we also try to correct, for example, for we try to mitigate the impact of interstellar reddening on these spectral line features. So, and therefore, so that's one of the reasons we locally normalized the extracted features. Now, by normalizing the spectra, we also lose some information, for example, on the effective temperature. So, and that's what we try to compensate for by directly using the GSP-FOT astrophysical parameters. So during the training of the algorithms, we we not only use these BPRP emission features, we also use the astrophysical parameters provided by GSP-FOT. And here it's important to keep in mind that we are during the processing, we have access to all the results of GSP-FOT, even those that might be a bit less reliable. So we are, and that will be filtered out a bit later during the post processing. So that's something we have to keep in mind, and that I will come back to that a bit later. So one of the features we extract is, of course, H-alpha, which is an important feature for most of these emission line star classes. And we go a bit further by integrate the information over the window we use to extract the feature. So to integrate the information, we use a very straightforward technique. So in order to make it a bit more robust and applicable to all the targets we have in the input, and it just consists in integrated the information between these two wavelength samples. So we draw a straight line between these 2 points, and we integrate this normalized information to get an estimate of the equivalent width of the H-alpha. So here I also want to remind some facts, is that at H-alpha in the RP, the resolution, the effective resolution is of 8 nanometer, and that the width of this wavelength sample is of about 2.5 nanometers. So meaning that all this information is spread over a certain number of wavelength sample, and that of course it limits the accuracy of the measurement of H-alpha we can achieve with this sort of technique. So another limitation, of course, that is related to that is, for example, for the cooler stars. So since we adapt the same definition of the H-alpha equivalent for all the stars, whatever the effective temperature, it has some impact on the measurement we can do on MK type stars. So, and to show that, I produced here at the lower part of the slide. So I show you some figures of M-type stars. So the observations are in blue here, and I also plotted the nearest marked spectrum, so synthetic spectrum I found. So I did this here for these two targets, and I noted here by this blue vertical line the position of the expected position of the H-alpha emission line if there is emission. So of course, when we see this for the first time, we could think, well, okay, there is emission here. But the truth is that it's just an effect of the blending of all these molecular bands that appear in these very cool stars. So here what we have is really the impact on the local pseudo continuum that we do not see, in fact, just due to the overlap of these different TIO molecular bands. And that has a direct impact on the measurement we do of the H-alpha, of this H-alpha equivalent. And it's also one of the reasons, because we know from the resolution and also from these very cool stars that we do not have direct access to the true equivalent width. We decided to name this equivalent width a pseudo equivalent width, because we know that the value we will have will be underestimated, and in some cases it will not correspond really to the equivalent width of the H-alpha line. So, and to show that a bit better, I represent here on the right the variation of the direct measurement of this pseudo equivalent width as a function of the effective temperature. So what we see here, so it's a density plot. So here, just to remind that even if it's a pseudo equivalent width, it still follows the same rules. So absorption is generally expected when the value is positive, and emission is expected when the value is negative. So what we see in this plot is that for the hot stars, the behavior is quite nice, and as we may expect from H-alpha. So we have a maximum at around 8,000 to 8,500 K, and it starts to reduce to about 0 when the effective temperature increases. When we go towards the cooler stars, then we have the same sort of trend. So the equivalent width of H-alpha is reducing to 0. We have a lot of scatter, but in the mean, it remains close to 0, as you would also expect, because for stars cooler than 5,000 K, we cannot expect any absorption from the H-alpha line. But once we are below 5,000 K, we see that the value becomes very, very negative, as we would mimicking a case where we would have, for example, emission in the H-alpha line. So, and that's exactly what I was showing here. So that's just an effect, a spurious effect of this rule we decided to follow to measure the H-alpha equivalent width. So this figure has been made by selecting about 2 million, so selecting randomly about 2 million of targets in the DR3 archive. So it's not exactly random because we try to get more or less a uniformly distributed effective temperature, which makes the plot a bit clearer than if you would just take the values randomly. So, and in this figure, what I'm showing is for exactly the same targets than in the previous plot, I show you the H-alpha measurement that has been done on the synthetic spectra. So as expected, it varies in the same way. So we see here this maximum for the A-type stars. We see here a broader variation here, which is due to the fact that the H-alpha line for hot stars is very sensitive to a variation of the surface gravity, while for the cooler stars, starting from the late A to F-type stars, this H-alpha line does not vary much with the surface gravity. So, and that's what we see here. It tends to 0 beyond 5,000 K, but directly as for the value we obtained on the observed spectrum, we start to have very negative value. And this value also start to depend on the surface gravity. Therefore, in order to try to mitigate this effect on the measured value, we decided to, again, use the astrophysical parameters provided by GSP-FOT to get the model value of the H-alpha line. So in this synthetic spectra, there is of course no emission that have been included, and we decided below 5,000 K to correct for this. So it's a sort of, we name that a correction, but it's just the fact that we subtract from the measured value, the value that we also measured in the synthetic spectra. So, and that we have that here. So that's what you see here. So we now have, even for the cooler stars, we have a mean value that tends to 0, as we would expect for these very, very cool stars. But also the counterpart is that we have much more scatter. So, and that makes it a bit more difficult to use than for the hotter stars, for example. So now what we store is the value that has been corrected. So here in this field, you will find the corrected value. So, and the corrected value means that for the hot stars, so above 5,000 K, the value is as it has been measured. So there is no model value that has been subtracted. But below 5,000 K, what you will find in this field is the value that has been subtracted by the model value. Now, that's not very important. For example, if you want to work directly on the measured value, because we also store for all the stars, even those for which we didn't apply this correction, we store the value measured on the synthetic spectra. And there is also a flag that tells you when the model value was subtracted, or was subtracted, so then the flag is equal to 1, or was not subtracted, in which case the flag is equal to 0, meaning that you can imagine some query of the archive that would enable you, for example, to correct all in this way all the stars, even the hotter ones, so which I did here. So here you see that the distribution change with a mean at around 0. So we may expect that all these negative values here, at least for the hot stars, are emission line stars. Or you can do the opposite and come back to the value that was measured by the module by applying the opposite receipt during your archive query, and in that case you would then get back this distribution. So this equivalent width is used during the classification of the ELS, but we also, before that, try to, so of course we expect, as I explained, we expect that the pseudo-equivalent width of H alpha we store in the astrophysical parameter table is not directly representative of the true H alpha equivalent width, and that is what we are showing here, where we compare systematically the pseudo-equivalent width of H alpha to some values that have been published by different people for different types of emission line stars. So, and what we note is that generally the pseudo-equivalent width is underestimating. So that's again something we were expecting. So, and it is underestimating by a factor of 2 to 3 the true H alpha equivalent width. Of course, this measurement, even with the correction, is still very bad for those stars with a very weak emission in the H alpha line, and more specifically for these chromospherically active M stars. So that's the figure I show here, where we cannot put any confidence in this value that we provide in the archive. So anyway, so one philosophy we followed is that we didn't apply any post-processing to these values provided and classifications provided by the ESP-ELS package, because I think they can still be worse if we want, for example, to study chromospherically M-type stars. So in a case-by-case situation, I think that it is still possible with the adapted synthetic spectra to correct and to make fruitful use of these measurements. So it's just a question of putting some more time on these on the analysis of these pseudo-equivalent width. So that's these are the comparisons that we have done during the validation. So here what you see is a fit in orange that so it's a linear fit we propose through the observed data. So the identity relation is provided by this blue line, but I also saw that there is a much more detailed comparison that was done with some LAMOS data. So with a more detailed relation between pseudo-equivalent width and true H alpha equivalent width from measured on the LAMOS data. So, and the trend is also more or less what I show here, 2 or 3 times. So the pseudo-equivalent width is 2 or 3 times smaller than what we may expect from H alpha. So this H alpha equivalent width is part of the ELS labeling. So here I show you the workflow of the ESP-ELS package and the classification of the ELS, the emission line stars, is performed by a series, by applying a series of two different random forest classifiers. So these classifiers are all trained on a combination of synthetic spectra and observed data. So synthetic spectra usually represents the population of stars without emission, while the observed data is used to represent the population of true emission line stars. So that's here the the complete workflow. So the spectral type tagging is done at first, but it is not directly used in the classification. It is used later in order to set the quality flag of the ELS labeling. But what we start to do is in the framework of this classification to compute the H-alpha pseudo-equivalent weight, then we apply a first random forest classifier that is trained specifically to detect the Wolf-Rayet stars and the planetary nebula. So all other stars receives a label unknown. Then once the Wolf-Rayet and planetary nebula are removed from the input, we continue to try to classify the remaining target. So if the star still needs to be classified, we check the pseudo-equivalent weight of the H-alpha line, and if emission has been detected, we start the second random forest classifier, which then provides the labeling of the H-alpha, purely H-alpha emitters, which are BE, R-big stars, T-Tauri stars, and chromospherically active M-type stars. So these results are saved, stored in the astrophysical parameters table also as a class label, but we also provide the individual probabilities we obtain for each of these 7 emission line star classes. So now what I'm showing here is a confusion matrix that has been produced using the test sample. So here it's important also to keep in mind that it's not just a result of one random forest classifier. It's really the confusion matrix that comes that results from the application of this whole workflow, so this series of 2 random forest classifiers, as well as this check on the H-alpha pseudo-equivalent weight. And this is the confusion matrix. So I will still show you a few other confusion matrices, and I try to use the same convention in all of these. So I think it's a bit important to explain how I made it. So in the ordinates, I put the expected classes of emission line stars, so which comes from this reference data set of emission line stars, and in the abscissa we have the predictions that have been made by the ESP-ELS module. The total number of reference stars or of test stars we use to test the algorithm are given here on the very right side of the confusion matrix. So it's the total of all the numbers you will see here, while the number of targets per cell is provided here by the top value you see in each cell. So meaning that, for example, here for the planetary nebula, so the number 98 means that over 670 true planetary nebula only 98 targets have been correctly classified. The other planetary nebulae have been classified as a star, because a lot of these planetary nebula spectra in Gaia are superimposed to the spectrum of the central star, and then if the emission feature is too weak, it doesn't go through the whole ESP-ELS algorithm. And that's a bit the case of a lot of the other emission line stars. So at a certain moment, the H alpha, so when I talk only about the H alpha emitters, a significant fraction of these emission line stars have too weak emission H alpha emission, which is too weak to really pass the detection threshold that has been defined in the ESP-ELS algorithm. So, and that explains, for example, why most of the T-Tauri stars have been classified as stars without any emission. So only a few survived the whole algorithm and were flagged as T-Tauri. So that's also, it's even more significant for the active M stars. So as I explained, so this H alpha measurement is very sensitive to the placement of the local continuum, and even with the correction, it still remains very sensitive to the template mismatch. So the mismatch you can have between the synthetic spectra used to correct the measured H alpha equivalent read and the true and the observations, in fact. So it's very sensitive to these template mismatches, which explains why most of the M-type stars have not been detected, and some which were detected have been confused with the T-Tauri stars. So confusion is another problem. So we try to use these, we use these GSP-FOT parameters in order to reduce the confusion. So it worked, but there is still confusion between the different ELS classes existing. So, and that's the case, for example, for the Air-big stars. So as you can see, which can be mixed up with B stars or T-Tauri stars. So while T-Tauri stars can also be mixed up with M-type stars, because some of these occupy the same place in the HR diagram. So now, again, as I told...
I'm sorry, Yves,
yeah?
it is 10:45, so you have 15 minutes left. Just a reminder.
Okay, sorry. Yeah, so in order to, so we didn't post-process the results. We kept all the results, but instead we use this quality flagging in order to identify the different cases where the labeling can go wrong. So, and we took into account, for example, the fact that in some cases the astrophysical parameters of GSP-FOT might be less accurate, or we can also take into account the fact that the astrophysical parameters provided and used for the classification are not consistent with the spectral type tagging. So here, what you see is an overview of the different classifications we have done for these 7 classes of emission line stars. So it's the distribution over the different values that can take these class label quality flag. So, and what is noteworthy is that, for example, for the T3 stars, a lot of the astrophysical parameters by GSP-FOT are thought to be less accurate than for the other types of stars. So all this detail is also provided in the online documentation and in some of the DR3 papers. So the spectral type, so ELS is also providing a spectral type tagging. So here we also use a confusion matrix to rate the spectral type tag that has been provided. There is a quality flag you can use to get an estimate of how confident we can be to in this spectral type tagging. It's the quality flag is the second digit of this flags underscore ESP-HS. And when we compare the results to SIMBAT, we usually get a fair agreement. Of course, we still have some confusion and contamination from the neighboring cells, but that is really expected since we used a very straight temperature threshold to decide what star is a B or O or a B-type star. So what is important here to see and keep in mind is that the agreement is relatively good, except maybe for the O and B-type star, where systematically, not systematically, but at least in half of the cases of the O-type stars are mixed with receives B-type spectral type tag. So that's the same sort of comparison, but this time done with the LAMOST data. So we provided using the same definition, temperature definition, a spectral type to all these LAMOST results. And here also, again, we see a fair agreement between the results of ESP-ELS and those obtained with LAMOST, except here for a few of these targets which received G, K, or M targets. So, and if we give a closer look to the data and that we cross-match it with the results obtained with the of the other modules, so we have this. So what I did here is just to extract the F, J, K type stars, which were apparently which received apparently a wrong spectral type tag, and I checked the effective temperature provided by GSP-FOT and GSP-SPEC. So, and what is obvious is that this spectral type tag seems to be consistent, at least with the results provided by the other modules. So meaning that here the problem is mainly due to cross-match issues between these two catalogs. So in the remaining cases for which GSP-FOT is providing hot star TF value, if we look to the H-alpha index, we see that most of these cases have emission. So most of the mistagging is due to this cross-match issues, while the remaining are probably due only to the presence of emission in the spectra of these stars. So now to put more emphasis on the confusion that we may have between O and B type stars. So I did the same work on the galactic O type star catalog to really show that a lot of these O-type stars have been labeled B-type stars. So the reason of this is not very clear to me. What I know is that this is not related to extinction. So it's just something to keep in mind when we, for example, want to select only O-type stars. We also have to take care of B-type stars and maybe cross-match with the with the other fields of the astrophysical parameters table. So now about the ESP-HS module. So we use synthetic, so it's based on the minimum distance method where we fit the XP and RES data. So we have here some details about the libraries that have been used, NLT for the hot stars and LT for the cooler ones. And the main assumption here we made for cycle 3 is that we fix the chemical composition to a solar value. Also, the other assumption is that we use extinction law, that is the one of Fitzpatrick, where we fix the extinction factor to 3.1, and we use some systematic comparison of synthetic to of simulations, comparison simulations to observed spectra in order to identify those parts of the spectra that seemed, at least for the synthetic spectra we are using, less accurate than the other parts. So just to focus on the more accurate part of the spectra, and we fit only these regions. So that is an overview of the results we have obtained. So in order to assess the quality of the data, so we compare it to survey data. So these plots are taken from the paper, so you will easily find these. So that's the paper Fresno and collaborators. So we see that the scatter is generally quite acceptable. I would say we have a fair agreement with the survey determinations, except for the hotter stars, where we generally note that values provided by the ESP-HS module tend to be underestimated. So the left part here is the residuals we have as a function of the effective temperature for the temperature, and the right is for the surface gravity with the dispersion values that I took here from the papers. So we made also some comparisons for clusters. So, and to do that, we use the color diagram. So here it's the color diagram of H Persei, of the H Persei open cluster, and we use the color diagram in order to locate the closest on the isochron, the closest point to the observed data, so that we can get an estimate from the isochron of the expected effective temperature and surface gravity. So I'm doing this job for a lot of these 42 open clusters, so we get 1,500 different measurements. We can also rate or assess the quality of the temperature and surface gravity values that have been provided by the ESP-HS, so which also confirms the conclusions we made based on the survey data. So now one thing is that about the completeness of the OBA sample we have, for which we have astrophysical parameters. So we noted that a lot of these hot stars are missing, and in order to put more emphasis to that, we try to estimate the fraction of detected OBA stars with astrophysical parameters from ESP-HS to the number of expected OBA star in different open clusters. So, and what we see here, so that's this fraction, is that the completeness is dependent on the interstellar reddening. So it's partly due to the interstellar reddening, and also probably due to the strong post-processing we applied, and which is based on the goodness of fit criterion. So yeah. So that's the results we obtained, an overview of the results we obtained for the interstellar reddening. So usually we have a good agreement between what ESP-HS is measuring and what we find, for example, for the clusters in the catalog of Kanta, Ego, and Godin. So we overestimate, however, a bit apparently the interstellar extinction, but we arrived to an opposite conclusion when we compare it star per star for the O-type stars, the extinction measured by ESP-HS to the value provided by Maïs Appellanites for these O-type stars. But in this work, they also take into consideration different values of the extinction factor. So while we are just assuming a constant extinction factor. So, and this explains why, so it's why I use this color coding, which represent the value that has been derived by Maïs Appellanites for the extinction extinction factor. And so we see that the agreement is directly dependent on this value of the extinction factor. So, okay, here I will go through a bit quicker because there is a paper that is discussing more specifically the line broadening. So CU8, so ESP-HS is also producing a value of this line broadening. The difference with what is provided in CU6 is that in CU8, we are working on coadded spectra. So meaning that we are also depending on the accuracy of the radial velocity measurements, which is a bit weaker for the hot stars, and also on the assumption we have to make on the LSF. So since it's a combination of different spectra obtained at different epochs with a different ELS, we make the assumption that the LSF is Gaussian. So, and that has an impact on the quality of the V sinusi value. Okay, so I will go. So that's my last slide, where I give you an overview of the different results that are produced by the two modules, and these are the plans for cycle 4. So we will try to provide not only a H-alpha estimate of the equivalent width, but also probability of emission. We also will use the RVS spectrum to put a label on the emission line star class. We will also take into account different metallicities, at least for the A and late B-type stars, to derive the astrophysical parameters, and we will propose a less restrictive post-processing. So thank you for your attention, and I apologize for taking too much of my time.